All right. Good morning, everybody. Hopefully you can you can hear me. We're going to pick up where we left off, and I'm going to. I know I sent out an announcement on Thursday, Wednesday or Thursday, um, letting you know which handouts to get, but I'm going to upload them here in the chat as well. Oh, shucks. I put one of them is in there twice. I apologize for that. All right, so one of them is the one entitled Workday. We're going to touch on that today, not initially, but we'll get to that today. And then reactions, excuse me, reaction stereochemistry. We're going to get to that either Wednesday or Friday. But you can go ahead and download it and have that handout ready. If you don't know where to find the handouts, let me share my screen right quick and show you again. We just want to go to Blackboard and in the folder entitled assignments. Let me go back. So you'll click on assignments, then you'll click on in-class handout submission, and then you'll see a folder for each section that we're going to cover. All right, so the first section is stereochemistry. All right, let me go ahead and share my iPad so we can pick up from where we left off on Friday. Not Friday, Wednesday. I apologize for that. Let's see. Give me 1 second. Sorry about that. Let me go ahead and share my iPad screen and we'll get started. Any questions about anything before we do get started? Let's install this plugin. Come on, man. Okay. All right. So where we left off on Friday, we were talking about Paxlovid and we're talking about chirality and how to identify chiral centers. We kind of touched on drawing mirror images, and we were going through this molecule and identifying these chiral centers and looking at the 4 different substituents that are attached to each center. And one of the things we talked about how to find the number of stereoisomers, right? If you have more than one stereo center, then you have the possibility of generating more than one stereoisomer. If you have one stereo center, you're only going to generate one other stereoisomer. But if you have more than one, then you have the possibility of generating other types of stereoisomers, which we're going to talk about today. One of the things that I didn't really stress, although it's important to kind of see it, when we talk about something being sp3 hybridized, we also have to understand that any center, be it carbon or some other atom that's not sp3 hybridized, cannot be a chiral center. So That's why when we were going through this molecule, we didn't look at the carbonyls, for instance, and to determine whether or not they were chiral, because those are all sp2, right? We didn't look at this nitrogen right here to determine if it was chiral because it's sp hybridized. So the hybridization state is one of the first ways to determine whether or not something can be a chiral center. So all of these are sp2. All right, so we don't count those. All right, so now let's get into, we talked about these, the number of stereoisomers. We said that for Paxlovid, the total number of stereoisomers is 64. And I want to talk about that now. I want to talk about the number of stereoisomers as it relates to this molecule, and what other stereoisomers are possible. So when you think about a molecule that has chiral centers, man, today is the 29th. Wow. Right. So you think about a molecule that has chiral centers. Let me just give you an example. So I'm just going to draw a simple molecule. I'm going to put 3 chiral centers in it. All right. So each one of each one of these carbons is a chiral center, right? So we can call that, we say that the way we determine how many possible stereoisomers are, or how many stereoisomers are possible for any given molecule containing chiral centers, is we use the equation 2 to the n, right, where n is the number of stereoisomers, right? So in this case, we have 3 chiral centers. So 2 to the third is going to be 8. So you have 8 possible stereoisomers, right? 8 possible stereoisomers, right? So I want you to think about this in terms of something we've already discussed, and that is the mirror image. We talked about that up top. We talked about non-superimposability, and we talked about the mirror image being non-superimposable. So for any chiral molecule, the mirror image is considered non-superimposable. So let's draw the mirror image for this. I'm just going to put a mirror plane here. And I'm going to draw it like I see it, right? The NH2 is going to be here, the bromine here, and then the OH here, like so. That's the mirror image, right? If we took it and turned it over, what would it look like? Somebody help me out. If I would have tried to align all the atoms, the nitrogen, the bromine, and the oxygen, what would that mirror image look like? If I took a spatula, put it underneath it, and flipped it over, what do you think? Don't all speak at once now. I know it's Monday.
Would it's like if you're flipping it with the N2 or the H2N now be on the right side.
Over here,
The,
like I have it drawn here.
yeah.
And then the bromine still gonna be here in the middle. But what I want you to notice is the orientation. So OH and NH2 were wedged, and then bromine is dashed. But when I turn it over, this is what it looks like right here. This is the mirror image. And so is this, right? down below, I just have it flipped over. Are y'all following that? So I took it and rotated it. It will be the equivalent of putting an axis through here and then just rotating around it to flip it over. If that helps. Right? Does everybody agree that what do you notice about the mirror image when I flip it over and draw it the way that I drew the original image? What do you notice about it? What happened to all of the chiral centers? Are they the same? If you look at this chiral center right here, if we look at that and that, is that the same? Are they going in the same direction? That's the point. That's the question I'm really asking.
No.
No, they're not. Everything in the mirror image is reversed. So all of your chiral centers get reversed. Everything.
So I have a question.
Come on.
The second drawing you drew at the top,
Mhm.
did you just, for the bottom drawing with the highlighter around it, did you just change the orientation of the atoms, but it's the same thing?
Yeah, I didn't change the orientation of the atoms. I changed the orientation of the entire molecule. I just flipped it over. I rotated it in space. It's like if you take your hand, look at the palm of your hand, and then if you're looking at the palm of your hand, flip your hand over and now look at the back side of your hand. That's all I did. I took it and I turned it over.
So is the second image and the third image the same thing?
Yes.
Okay, all right.
Yes.
Okay.
Great question. Those are the same images or the same molecule. They're just reoriented in space. If that makes sense. All right. So with the mirror image, this is a defined stereoisomer. We call the mirror image the enantiomer. Right? That is a non-superimposable mirror image. Right? Non-superimposable mirror image. It's called an enantiomer. So the mirror image of any chiral molecule is called the enantiomer. And in the mirror image, this is very important, all of the chiral centers are reversed. I'm going to explain reversed in a second. All right. So all your chiral centers have a different, what we call configuration. All right, so let's look at that. So in the enantiomer, I'm going to draw the first image first. Let me draw that. So this is OH. This is NH2. And this is BR. And the mirror image is going to look like the exact opposite of that. OH, NH2, BR. Right, this is the mirror image. All right. Now, each one of these, we keep talking about chirality and stereochemistry and all this stuff. And we said that a stereoisomer has the same structure, but a different 3D orientation. So you can see that these two are indeed stereoisomers. They have the same exact structure, but the chiral centers are oriented differently, right? So every chiral center has a configuration. Every chiral center has a configuration. It's either going to be R, or if you watch the video, you should have had some exposure to this already. It's either going to be R or S. So R is going to be clockwise, and then S is counterclockwise. So I'll say CW and CCW, clockwise, counterclockwise. And what that means is the R and S refers to how the groups are oriented around the chiral center. So this is, I'm going to say attached. So how groups are attached to the chiral center. All right. So if you look here, let's start with this one. This is my chiral center. I have 4 groups attached. One of them is hydrogen. So I have OH, hydrogen. I have a carbon here and a carbon here. Now, one of those videos I sent dealt with how to determine the configuration based on the groups that are around it. And we have to do what's called assigning priority. So that's 1 through 4, and it's based on what? And somebody tell me that.
The mass.
Atomic mass or atomic number. So we're gonna say atomic. All right, atomic mass. Okay. So if we look at these 4 groups, right? That's a carbon, that's carbon, okay, hydrogen, and then oxygen. We're only concerned with the group that's directly attached to the chiral center. So of those 4 groups, which one, and I did not define priority. 1 is the highest, right? And then 4 is the lowest. So of those 4 groups that we just outlined, which one has the highest priority on that stereo center that we're looking at, the one that's highlighted in teal?
Oxygen.
Oxygen, right? So this is priority 1. And then hydrogen is always going to be 4, unless there's a lone pair present. The only group that's lower in priority than hydrogen is a lone pair. So when you see a hydrogen, you can automatically assume that that's going to be the lowest priority group. All right, now we have to choose between 2 and 3. We have two, both of those are carbons. So anytime you have 2 carbons and you have to determine the priority, you have to look at the next group that's attached to it. So for this carbon on this side, right, this is actually a CH3, because the end of every line is a CH3. Right, so the next group attached here is hydrogen, and then carbon on the other side, right here, the next group attached is bromine. Yes, it does have a hydrogen, but there's no sense in comparing hydrogens because we know that it's a moot point. They have the same exact atomic mass, so it's kind of a moot point. So go to the next atom if you have 2 atoms that are identical. So in this case, the carbon over here is going to be 2. And that'll make by default this carbon 3. Any questions about that? All I'm doing is looking at the atoms that are attached to the chiral center, and I'm assigning priority based on their atomic mass. And here's another thing that always comes up, and I always have to caution students about it. Don't add the atoms together. So that CH3 that's on the end, the mass is not 15, right? It's 12. You don't add the other hydrogens to it. Same with OH, you don't add that hydrogen to it and make it 17. The mass is 16, right? So if you look at the molecule itself, right, and look at that chiral center, now once I assign priority, I just need to count to 3, right? The 4th group is always, you always want that away from you, and it does not, you don't count it when you're assigning configuration. So we assign priority first, and then once we prioritize, then we can determine whether it's R or S, right hand or left. And hopefully that's making more sense now. When I count to 3, am I counting in a clockwise fashion or a counterclockwise fashion? That's the question. And that's going to tell me if it's R or S. So here, what do you see? We got, this is 1, this is 2, and that's 3. Is that clockwise or counterclockwise?
Clockwise?
It's clockwise. Good. So now that means that this stereo center right here is R. Are we following that? Any questions about that? The priority part is the easiest part, because that's, if we learned about, you can look at the periodic table and find the atomic masses in seconds, right? The other part is how the groups are oriented around that chiral center. All right, so then that's the part that's a little bit more difficult, figuring out whether it's clockwise or counterclockwise. All right, let's do the nitrogen, the center that has nitrogen on it, and then we'll do the bottom one, and I'm gonna use that to make a point. All right, so let's go to here. Where are my 4 groups? There is a hydrogen that's on here. It's not shown, it's understood to be pointed back. So is this a group right here, that carbon? The chiral center is the carbon that I have highlighted. So the 4 groups attached will be that, the carbon I have circled, the hydrogen, the NH2, and then this carbon over here, which just happens to be bound to both chiral centers, that the first one we looked at and this one. All right. How do we prioritize that? What do you think is going to be one out of those 4 atoms? Nitrogen, carbon, carbon, and hydrogen. Which one has the highest atomic mass?
Nitrogen.
Nitrogen. So this is going to be 1. I'm going to call that 1. All right, I don't like that color. And then hydrogen is 4. The only thing lower than hydrogen in priority is a lone pair. Now we got to pick between the other 2 carbons as 2 and 3. What do you think? It's a similar scenario to what we just saw, right? We have a CH3 on the end here. Right, and then you have that carbon in the middle that's bound to bromine. All right, which one is going to be 2? Based on what we just
carbon with the bromine
the one in the middle. Excellent. This one, that's 2. Right, the reason it's 2 is because when you have 2 atoms that are identical and they have the same atomic mass, you have to go to the next atom until you reach a point of difference. Right, so the point of difference is the bromine. You don't have to keep going all the way out. The first point of difference you reach, that's where you can stop. All right, so bromine, that carbon with the bromine attached is 2. That makes this 3. Now, all we're looking at is the top 3 groups. We don't care about 4, and 4 is already pointed back into the page, so it's irrelevant to us in determining configuration. So is that clockwise or counterclockwise? If I'm counting from 1 to 2 to 3, is it clockwise or counterclockwise?
Counter.
It looks like it's counterclockwise. That's exactly right. So if R is clockwise, counterclockwise is the opposite. So this center is going to be considered have a configuration what we call S. In Latin, the S stands for sinister, which means left hand, and the R stands for rectus, which means right hand. Right. So this is counterclockwise. So we're going to call it S. So the configuration of that stereo center is S. Any questions about that? All right, now let's do the one in the middle. So I'm going to erase some of this stuff. And hopefully you're taking notes, or at least kind of jotting down the example. All right, let's do the one in the middle. That so this carbon right here, this is the one we're looking at now. Right, the bromine obviously is going to be 1. because it's larger than the fourth group here is hydrogen. I don't have it shown, but if bromine is on a dash, which direction is the hydrogen pointing? On that carbon. If the bromine is going back into the page, that's what the dash line means. Which
Towards
way
it.
is the hydrogen pointing?
Like towards us on a wedge.
Wedge. Good, excellent. So there's a hydrogen there. So we know that's going to be 4. We know this is going to be 1. Now the question is, what's 2 and what's 3? Right. So I'm going to look at this carbon because that's attached to that chiral center and this carbon. Are we following that? Where's my point of difference? Because both of those are carbons. So I need to go to the next atom. If I look at I should have made these different colors. Hold up. Let me do that. Now on the pink side, if the next atom is oxygen, is that right?
Yes.
And on black side, the next atom, I'm just trying to find the point of difference because both of those are carbons. So I can't assign priority if both atoms have the same atomic number. So on the left side where it's pink, I go to the next atom, which is oxygen. On the right side is nitrogen. Which of those two, which one has a higher atomic mass?
Oxygen.
Oxygen. So that means that this carbon over here is going to be 2. And then by default, the other carbon on the other side is going to be 3. That's really messy. All right. But here's my priority. Here's my priority for this stereo center right here. This is 1, that's 2, and this is 3 on this side. Now, how do we count that? If we just count it to 3, is it clockwise or counterclockwise?
Clockwise.
It is clockwise, yes. But we have a caveat here, and it's here. So when the fourth group, because normally when you're assigning configuration, once you assign priority, you want to rotate the molecule so that group 4 is away from you. I know you saw that in one of those videos. But in this case, since the fourth group is coming out at us, we're going to reverse what we see. I'm going to write that in here. Let me write it on this side. This is getting really cluttered. So we're going to reverse I'll say configuration. So group 4 is on a wedge. And when I was first started teaching, I would never teach this as a shortcut. I would always build a model and have you hold it in your hand and turn it away from you. But over the years, I've rarely encountered an instance where this didn't work. So now this is the way I teach it. Plus it makes it doesn't take as long to get this point across. So we said that it's clockwise as we see it. Is that right? Which would be what if we say it's clockwise? R or S?
R.
R. But because the H is on a wedge, we're going to reverse that. So that central stereo center, instead of it being R, because the groups are oriented in a clockwise fashion, we're going to call it S. So I'm going to erase a lot of this stuff. Actually, you know what? I'm just going to redraw it or copy it. Because I know I don't want to delete anything, and then when you come back and look for it, you can't find what was on there. So now we said the first one was S, is that right? No, this was R. This was what? S, and we said this one is also S. Yes.
Yes.
So the first stereo center is R, the middle one is S, and the outer one is also S. Based on what we did up here, I know it looks sloppy and messy, but you have to resolve each stereo center separately. So every one of them, every chiral center, you have to look at them individually. Okay, questions, any questions? So you prioritize, and then once you prioritize, you count to 3, right? If the fourth group is already on a wedge, or already on a dash, you keep what you see. If the fourth group is on a wedge, the low priority group is on a wedge, then you reverse it. I'm gonna write that down over here.
I got a question.
Go ahead.
I'm not sure if you mentioned this, but how do we know if, like, for, you know how you said like reverse it,
Mhm.
or if the hydrogen is on a wedge, how do we
Mhm.
know if the hydrogen is going to be on a wedge or on a dotted line?
Or dash, it depends on what the other group on that carbon looks like. So like right here on this carbon, how the OH is pointed back on the dash,
Mm-hmm.
then the hydrogen is automatically by default going to be on the wedge.
Okay.
And the same with this group. And then here with the bromine on the wedge, the hydrogen is on a dash by default.
Okay.
Great question. All right, let's see. What was I saying? If the lowest priority group is dashed. I'm gonna put dashed in quotes. If it's wedged. So normally the way we refer to this is like if it's on a dash, it's back. If it's on a wedge, it's up. All right, and then so you reverse it, right? So when you assign priority, oh, not priority, configuration. Sorry about that. Let me fix that. So when you assign a configuration, if the group if the lowest priority group is on a dash, when you count to 3, you just keep what you see. If it's on a wedge, when you count to 3, you reverse it. So if it's on if the low priority group is on a wedge, like we just did that example in the middle, and we said that it looked like it was R because it was clockwise, but we had to reverse it because of that hydrogen being on a wedge. All right, now here's the question, the other part of this, right? If I look at the mirror image, what are the configurations of the 3 stereo centers in the mirror image? Right? If I know the configurations over here, then I know what the mirror image is automatically without having to even do anything, because the mirror image is by default the opposite of the original image. So the first stereo center in the original image was R. What is it in the mirror image? By default,
Okay.
it's S. It's got to be the opposite, right? What about the middle one? We said it was S in the original image. What is it here?
R.
R by default. Don't be afraid to say that. What about the stereo center where nitrogen is? What is it in the original image? It's S, right? We just determined that. So what is it in the mirror? It's got to be R, right? By default. Are y'all following that? I didn't have to do anything to this one, because once I figure out the original, I can determine the other one, the mirror, just based on reversing everything that's in the original, because we just said that up here, that all the chiral centers get reversed in the mirror image. So if it's RSS in the original, then the mirror has to be SRR. That's the configuration. So the 3D orientation for every chiral center in that molecule is different, if that makes sense. Questions? Any questions? All right, let me introduce one other topic based on this. So up here, we said that there were 8 possible stereoisomers. Is that right?
Yes.
Mhm.
Yeah.
8 possible. How many do we have down here so far? We have a original image. We have a mirror image. Is that right?
Yes.
How many are left? If we got 2,
6.
we got 6 left that we need to figure out what they are. All right, so now I'm gonna introduce you to another topic, another type of stereoisomer. Uh-oh. And that is what we know as a diastereomer. Diastereomer. Excuse me. All right, and a diastereomer is not a mirror image. Okay, that's the right. It's not a mirror image, but it is a stereoisomer. So let me show you what a diastereomer would look like. So if I take the original image that we started with, Br NH2OH, this is the original. A diastereomer of this would look like this, right? I would take this. I only well, I'll show you. What did I change in the other image? First of all, is this image a mirror image of the original, of the first one?
No.
It's not. If it were, everything would be different. But what did I change? I only changed this one stereo center, didn't I? That's the only difference between those two. So that's what a diastereomer is. It is a stereoisomer that differs by one stereo center, right? So you take one stereo center and you alter it. Are y'all following? Yes, no, maybe? So all I did was change that first stereo center from wedged to dashed. And now I have a diastereomer. And I have my 4th image. Now, what else can I change? What if I leave the first one like it is, but change the second one? Are y'all following that? Yes, no? What did I change from the original?
You made everything on the wedge,
Yeah.
like the bromine.
So I changed the bromine. I changed this one now, right? I left the first one how it is. I changed the middle one. And then if I did that again, you can see where I'm going with this. It's kind of like I'm only going to change one at a time. So I'm going to leave this. Sorry about that. So that's BR. I'll fix that before I post it. All right. Following? Now I changed this one. Left the other two the same. Yes or no? So each one of these are what we call diastereomers. They're all diastereomers. Okay. Now, how many images are here? Based not counting the original. How many images do we have?
3.
3. How many more stereoisomers are we looking for again? 6. Is that right?
Yes.
Yeah.
So what would you do to get the other 3 stereoisomers?
Reverse these.
Who was that? Speak up.
reverse them? Would you reverse these?
You would draw, so when you say reverse, excuse me.
The mirror image, I guess.
Yes, you would draw the mirror image of each one. Is that what you're saying?
Yeah,
Okay, who is that?
Asia.
Hey, all right, put your Cash App in the chat. I'm buying you lunch today. You're exactly
Oh,
right.
that.
Each one of these diastereomers has a mirror image. So that's where your other 3 isomers are going to come from. So we said 8 total. We had the original and its mirror image. And now we got these 3 diastereomers, and each one will have a mirror image. And we're not going to have time to draw them. So I want you to draw them. I want you to draw them. All right. So then, thank you. When we have a chiral center or multiple chiral centers, then we have the possibility for multiple stereoisomers. When that's the case, then we also have to think about what those stereoisomers are. They're either going to be enantiomers or diastereomers. Enantiomers are mirror images. Diastereomers are not mirror images. So these 3 are what we call diastereomers, and each one of those is going to have its own mirror image. And so that's how you get your 8 stereoisomers. Now let me go back up to here. Oh, before I do that, any questions about that? Because we're going to wrap this up right here, and we'll hit the handout. We'll start on the handout on Wednesday, God willing. Any questions about that? All right, let's go back up to here. If I drew the mirror image of Paxlovid, did I have it twice? I did not. If I drew the mirror image of Paxlovid, what would happen to all the chiral centers that are present? Anybody?
Can you ask the question again?
If I drew the mirror image of Paxlovid, what would happen to all the chiral centers that are present?
Would they flip?
They would all flip. That's exactly right. If I changed this one right here and left the rest the same, what would that image be? Or what would that isomer be considered? Would it be a mirror image or an enantiomer, or would it be a diastereomer? If I only changed this one that I just circled with the nitrogen and left everything the same,
The diastereomer?
it would be a diastereomer. If I changed one of the other chiral centers and left the rest of them the same, what would that be? That would also be what? A
Diastereomer.
diastereomer. Are you following? So that's how we get these 64 isomers, stereoisomers. Because first of all, you're going to have the mirror image, and then you got multiple stereo centers that you can alter to make different diastereomers, and each diastereomer is going to have its own mirror image as well. Right? But again, when you're making a molecule like this, it's very specific, right? Because it's binding to some receptor or something in a cell that is disrupting some pathway. So you need this one and not the other 63, right? But you have a possibility of all 64. It just depends on your method for making it. All right, we got to stop here because I think my iPad is going to die. It's on 1%. I need to let it charge before my next class. Any questions about anything?